Please subscribe to support the channel. Black holes are the universe's most captivating mysteries, regions of space where gravity is so powerful that not even light can escape. They warp time, devour matter, and challenge our understanding of physics itself. Among them lies a cosmic titan so massive, it almost seems impossible. TON 618. This black hole, over 66 billion times the mass of our Sun, is the largest ever discovered. A brilliant, blazing beacon at the heart of a distant quasar, shining brighter than entire galaxies. It's a reminder that, while humanity has mapped the stars, we've barely begun to grasp the true scale of the cosmos and the monstrous wonders that lurk within it. To understand the true nature of TON 618, we first need to understand what a black hole actually is, not just in theory, but in the deepest sense of what it represents about our universe. A black hole is, at its core, a region of space-time where gravity has become so overwhelmingly strong that nothing, not even light itself, can escape its pull. It's not a hole in the conventional sense, not a tunnel or a doorway, but rather a place where the laws of physics, as we know them, simply break down. Imagine the very fabric of space being stretched, curved and folded until it collapses in on itself. That is a black hole. The story begins with the death of a massive star. When a star many times larger than our Sun exhausts its nuclear fuel, it can no longer resist the inward pull of its own gravity. The outer layers are blasted away in a supernova, while the core implodes, collapsing under its immense weight. If the collapsing mass is large enough, the force becomes unstoppable, crushing the star's matter into an infinitely dense point, a singularity. This singularity is a place of infinite density and zero volume, where time, space, and all known physical laws cease to function in any meaningful way. It's a mathematical boundary where our equations can go no further, a frontier beyond which physics, as we understand it, disintegrates. Surrounding the singularity is the event horizon, a boundary that defines the point of no return. Anything that crosses this invisible line, a particle, a photon, or even an entire planet, is lost forever to the black hole's grip. From the outside, nothing seems particularly unusual about the event horizon. It doesn't glow or shimmer, but what makes it so extraordinary is that it marks the place where escape becomes impossible. The escape velocity there, the speed you'd need to flee the gravitational field, exceeds the speed of light. Since nothing in the universe can move faster than light, this means that once something crosses the horizon, it can never come back out. Yet, the black hole doesn't simply suck things in indiscriminately, as often imagined in science fiction. If our Sun were replaced by a black hole of the same mass, the planets would continue orbiting exactly as they do now. They just wouldn't receive any light or heat. The real strangeness happens close to the event horizon, where gravity becomes so extreme that it distorts both space and time. Time slows dramatically near a black hole. From an outside observer's perspective, an object falling in would appear to freeze just before the event horizon, fading from view as its light is redshifted into invisibility. Meanwhile, for the object itself, time would continue normally, right until it's torn apart by tidal forces, stretched into a stream of atoms in a process known as spaghettification. What's even more fascinating is that black holes don't exist in isolation from the universe. They are deeply connected to its evolution. They are not just cosmic monsters devouring everything nearby, they also help shape galaxies, influence star formation, and even regulate the growth of cosmic structures. The energy they emit, in the form of X-rays and powerful jets of plasma, can heat surrounding gas clouds and sometimes even prevent new stars from forming. In this way, black holes act as both creators and destroyers, sculpting the galaxies that we see scattered across the night sky. Black holes also reveal the deepest relationship between space, time, and gravity, the very concepts that Einstein's theory of general relativity redefined. According to Einstein, massive objects curve space-time around them, and what we perceive as gravity is simply the motion of matter following these curves. A black hole represents an extreme of this curvature. It's as though space-time itself has been pulled so tight around the singularity that it folds inward, sealing off that region from the rest of the universe. Inside, the direction of space and the flow of time effectively switch roles. Movement forward in time inevitably means moving closer to the singularity. There is no path that leads outward again. Interestingly, black holes are not entirely black. In 1974, physicist Stephen Hawking proposed that they emit faint radiation, now known as Hawking radiation, caused by quantum effects near the event horizon. Over incomprehensibly long timescales, this could mean that black holes slowly evaporate, losing mass until they eventually vanish. Per supermassive black holes like TON 618, this process would take far longer than the current age of the universe, but it adds a fascinating twist to the story. Even these seemingly eternal objects are not truly immortal. The size of a black hole depends on its mass, and their masses can range across a staggering scale. The smallest, known as stellar mass black holes, form from the collapse of single massive stars and typically have a mass between a few and several dozen times that of our Sun. These are scattered throughout galaxies, often detected by their interactions with companion stars. The next category, intermediate black holes, bridge the gap, hundreds to thousands of solar masses, though they are harder to detect and less well understood. And then at the top of this cosmic hierarchy are the supermassive black holes, giants that sit at the centers of galaxies, containing millions or billions of solar masses. It is among these supermassive black holes that TON 618 holds its throne. Its gravity is so intense that it has shaped not only the space around it, but the very light that escapes its vicinity. The radiation emitted by the matter spiraling towards it has traveled across billions of years to reach us, allowing astronomers to glimpse what is perhaps the most extreme object in the known cosmos. TON 618 isn't just a black hole, it's an empire of gravity, surrounded by storms of gas and radiation, brighter than almost anything else in existence. But before we can explore TON 618's staggering scale and blinding radiance, we need to understand how black holes differ from one another, because while they all share a similar structure, the processes that create them and the ways they grow vary dramatically. Each type of black hole tells a different story about the life and death of matter in the universe. And to understand how TON 618 reached its unfathomable size, we must first look at that cosmic family tree. Black holes come in many sizes, but they all share one common trait: an insatiable hunger for matter and energy. The universe, in its vast diversity, has produced black holes ranging from the remnants of dying stars to the titanic engines that power entire galaxies. By understanding the different types of black holes, we can better appreciate how TON 618 became the ultimate cosmic colossus, the crowning example of just how massive and powerful these entities can become. Let's begin at the smallest end of the cosmic scale with stellar mass black holes. These are the most common type, formed when massive stars, typically more than 20 times the mass of our Sun, reach the end of their lives. When such a star runs out of nuclear fuel, the delicate balance that has kept it stable collapses. The gravity-collapsing mass of a stable gravity takes over, crushing the core in a fraction of a second. The outer layers are blasted away in a supernova, leaving behind a compact, incredibly dense core, a black hole. Most stellar mass black holes weigh between 3 and several dozen solar masses, though some exceptional cases reach up to around 100.
Despite their relatively small size, stellar mass black holes are among the most extreme objects in the universe. A single teaspoon of their material would weigh billions of tons. Many of these black holes are found in binary systems, paired with a companion star. When that companion wanders too close, the black hole begins to strip away its outer layers, feeding on the gas that spirals inward and forming a glowing accretion disk. The infalling material heats up to millions of degrees, emitting intense X-rays that astronomers can detect. In this way, we've discovered numerous stellar black holes scattered throughout our galaxy, unseen yet blazing in high-energy wavelengths, quietly shaping the cosmos one meal at a time. Then there are the intermediate mass black holes, a rare and mysterious class that bridges the gap between the small and the enormous. Their masses range from a few hundred to a few 100,000 suns. Scientists believe these may form through the merging of smaller black holes or the collapse of massive star clusters. But finding them is no easy task. They're elusive, hiding in the dark corners of galaxies, and don't often produce the kind of bright radiation that makes other black holes visible. A few promising candidates have been discovered in dense star clusters and dwarf galaxies, faint hints that nature may indeed produce black holes on every scale. The existence of intermediate black holes also helps explain a crucial cosmic mystery. How did supermassive black holes form so quickly in the early universe? Galaxies observed less than 1 billion years after the Big Bang already host black holes with billions of solar masses. That's far too fast for them to have grown from ordinary stellar remnants alone. So the current theory suggests that intermediate mass black holes may have acted as seeds, merging, feeding, and rapidly accreting material in the dense young universe until they became the giants we observe today. And that brings us to the supermassive black holes, the undisputed monarchs of galactic centers. These titans contain millions, even billions of times the mass of our sun. Unlike their smaller counterparts which form from dying stars, the origins of supermassive black holes are still a topic of intense research and debate. Some may have begun as the direct collapse of enormous gas clouds shortly after the Big Bang. Others might have grown gradually, feeding on gas, dust, and even entire stars over billions of years. However they form, their presence is universal. Nearly every large galaxy, including our Milky Way, hosts one at its core. Supermassive black holes are more than just gravitational wells. They are cosmic architects. Their immense energy output can shape the evolution of their host galaxies. As they feed, they generate powerful jets of charged particles that blast across interstellar space, sometimes stretching for hundreds of thousands of light years. These jets can heat surrounding gas and regulate star formation, effectively controlling the growth of galaxies themselves. In this way, supermassive black holes act as both destroyers and nurturers, balancing the cosmic ecosystem in ways we are only beginning to understand. At the center of our own galaxy lies Sagittarius A, a relatively modest black hole weighing about 4 million suns. Even so, its gravitational influence holds the Milky Way together, anchoring billions of stars in their orbits. A step up in scale brings us to M87, the first black hole ever imaged, sitting 53 million light-years away with a mass of around 6.5 billion suns. When the Event Horizon Telescope captured its now iconic shadow in 2019, humanity caught its first real glimpse of the dark heart of a galaxy, a glowing ring of light orbiting an invisible abyss. But compared to TON 618, both Sagittarius A and M87 seem almost small. TON 618 isn't just a supermassive black hole, it's a hypermassive black hole, a category so extreme that only a handful of candidates even come close. With a mass estimated at 66 billion times that of the Sun, TON 618 sits atop the cosmic food chain. Its event horizon would be larger than our entire solar system, and the energy radiating from its accretion disk outshines thousands of galaxies combined. It's not merely the biggest black hole ever found, it's the largest known single object in existence. What's even more mind-bending is that TON 618 lies over 10 billion light-years away, meaning we're seeing it as it was when the universe was still young, less than a third of its current age. Somehow, in that relatively short cosmic time, it already had grown to unimaginable proportions. This fact alone challenges our understanding of how black holes evolve. It suggests that in the early universe, conditions may have been ripe for rapid growth, perhaps through violent mergers, torrential infall of gas, or mechanisms that allowed matter to accrete faster than the limits we see today. In many ways, TON 620 is the final evolutionary stage of this hierarchy, the ultimate destination of black hole growth. It embodies everything extreme about these cosmic objects: the deepest gravity, the brightest radiation, and the most powerful influence over its environment. When we look at TON 618, we're looking at the very boundaries of what nature can create. But TON 618 wasn't discovered as a black hole at first. In fact, its story began in a completely different context, not as a dark object swallowing light, but as an impossibly bright beacon shining across the depths of space. To understand how we found it, we have to go back to the mid-20th century, when astronomers scanning the sky for radio sources stumbled upon something so luminous, so extraordinary, that it would take decades before they realized what they were truly seeing. The story of TON 618's discovery begins not with the search for black holes, which were still a theoretical curiosity at the time, but with the exploration of the skies in radio waves. The mid-20th century marked a new era in astronomy. For centuries, humanity had relied on visible light to study the heavens, but with the advent of radio telescopes, astronomers began to see the universe in a completely different spectrum. Suddenly, the night sky was revealed not as a quiet tapestry of stars, but a bustling arena filled with energetic phenomena, pulsars, nebulas, galaxies, and mysterious sources of powerful radio emission that defied explanation. It was during this pioneering period, in the 1950s, that a team of astronomers conducting surveys at the Tonantzintla Observatory in Mexico cataloged a faint but unusual object in the constellation of Canes Venatici. They noted it as part of a list of radio sources, designating it TON 618, where TON refers to the Tonantzintla Observatory and 618 was simply its entry number. At the time, its true nature was completely unknown. It appeared as a faint, bluish star-like point of light in optical observations, not particularly remarkable except for the fact that it coincided with a powerful radio source.
In the 1950s and early 1960s, astronomers were encountering more and more of these radio stars, objects that looked stellar through a telescope but emitted enormous amounts of radio energy. The term quasi-stellar radio source was coined to describe them, soon shortened to quasar. These quasars baffled scientists. Their light spectra showed strange emission lines that didn't seem to match any known elements. It wasn't until the early 1960s that astronomer Martin Schmidt made the breakthrough realization. Those lines were actually hydrogen lines, shifted dramatically by the cosmological redshift caused by the expansion of the universe. That insight changed everything. It meant that quasars were not nearby stars at all. They were distant, incredibly luminous objects, so far away that their light had been traveling toward us for billions of years. Their brightness was almost unthinkable. For an object to appear as bright as a star while being billions of light years away, it had to be releasing energy on a scale far greater than an entire galaxy. TON 618 fit perfectly into this category. Follow-up studies revealed that it was one of the most luminous quasars ever detected. Its light spectrum showed strong emission lines from highly ionized gas, evidence of temperatures and energies that could only be produced by extreme gravitational processes. Though the term black hole was just entering the scientific lexicon around that time, the theoretical framework was already being built. By the late 1960s, researchers began to realize that quasars could be powered by supermassive black holes feeding on infalling matter. As the idea took hold, astronomers re-examined objects like TON 618 under this new light. What they saw was staggering. The energy radiating from TON 618 could not be explained by nuclear fusion or stellar processes. It had to come from gravitational energy. The only plausible engine powerful enough to generate such luminosity was a supermassive black hole consuming matter at a furious rate. Decades later, as instruments and techniques improved, the true scale of TON 618 began to emerge. In the 1980s, spectroscopic observations of its emission lines allowed astronomers to estimate the velocity of the gas swirling around its unseen core. Using those velocities and the physics of orbital motion, they calculated its mass, and what they found stunned the scientific community. TON 618 appeared to harbor a black hole with a mass of approximately 66 billion suns. To put that into perspective, if the sun were the size of a marble, TON 618 would be comparable to a sphere tens of kilometers across. Its event horizon, the boundary beyond which nothing can escape, would be so vast that light itself would take days to travel across it. It wasn't just another quasar. It was a cosmic giant, a record-breaking anomaly that pushed the limits of what astronomers thought possible. But even as scientists recognized the immensity of TON 618, questions arose. How could something so massive have formed so early in the universe's history? The light we see from TON 618 today began its journey roughly 10.4 billion years ago, meaning we are observing it as it was when the universe was only about 3 billion years old. Somehow, in that short cosmic window, it had already reached the size that dwarfed nearly every other known black hole. This single fact challenges our understanding of black hole growth and galaxy evolution, hinting that the early universe was far more dynamic and perhaps far more violent than we once believed. Today, TON 618 remains one of the most luminous quasars known, and its discovery stands as a testament to the power of human curiosity and ingenuity. From a faint radio blip on a mid-20th century sky survey to one of the most awe-inspiring entities ever identified, its journey mirrors our own, a path from ignorance to revelation, from mystery to understanding. What makes TON 618 shine so brilliantly is not the black hole itself, but the material swirling around it. Gas and dust heated to unimaginable temperatures as it falls toward oblivion. To truly grasp why TON 618 burns so brightly, we need to explore the nature of quasars themselves, these dazzling cosmic lighthouses that reveal the presence of the universe's deepest darkness. A quasar, short for quasi-stellar radio source, is one of the most extraordinary and powerful phenomena in the cosmos, a blinding beacon of energy that can outshine entire galaxies. Despite their star-like appearance in early telescopic observations, quasars are not stars at all. They are the intensely bright cores of distant galaxies powered by supermassive black holes that are actively consuming vast amounts of gas, dust, and even entire stars. When matter falls into a black hole's gravitational grip, it doesn't plunge straight in. Instead, it forms a swirling accretion disk that heats up through friction, releasing tremendous amounts of radiation. The result is a cosmic furnace that radiates light across every wavelength, from radio waves to visible light, ultraviolet, X-rays, and even gamma rays. In essence, a quasar is a galaxy in the throes of feeding its central black hole, a galactic heart burning at unimaginable brightness. The amount of energy produced by this process is staggering. Just a few solar masses of matter converted into energy through accretion can release more power than all the stars in the Milky Way combined. To put that in perspective, while our sun converts only a tiny fraction of its mass into energy over billions of years, a quasar can convert entire stars into pure radiation in relatively short bursts of cosmic time. The light from a quasar originates from a tiny region compared to the galaxy it inhabits, often smaller than our solar system. Yet, it can outshine the galaxy's hundreds of billions of stars. The incredible brightness makes quasars visible across vast cosmic distances, turning them into beacons that help astronomers map the early universe. When we observe a quasar, we are looking deep into the past, seeing the light that left it billions of years ago. Many of the quasars we detect today existed when the universe was young, less than a tenth of its current age, meaning they offer a direct glimpse into the universe's formative years. At the core of each quasar lies a supermassive black hole, surrounded by its accretion disk, a maelstrom of matter spiraling inward at nearly the speed of light. As this material orbits the black hole, immense gravitational and magnetic forces tear it apart, generating temperatures of millions of degrees. The radiation emitted by the accretion disk ionizes gas in the surrounding regions, producing the broad emission lines that astronomers can detect in the quasar's light spectrum. These emission lines act as fingerprints, allowing scientists to identify the elements present and measure how fast they are moving. Some quasars also produce colossal relativistic jets, streams of charged particles ejected from the poles of the black hole's magnetic field at nearly the speed of light. These jets can extend for hundreds of thousands of light years, slicing through intergalactic space and influencing the gas and galaxies they encounter. In many cases, these jets are responsible for the intense radio emissions that led to the discovery of quasars in the first place. TON 618 was one such object. a faint optical source with an unusually powerful radio signature, later revealed to be one of the brightest quasars ever observed. The brilliance of a quasar like TON 618 doesn't come from the black hole itself. Black holes, by definition, emit no light. Instead, it's the result of gravitational energy being converted into radiation as matter spirals inward. The efficiency of this process is astonishing. Accretion around the black hole can convert up to 10% of the infalling matter's mass into energy, far surpassing the efficiency of nuclear fusion, which powers ordinary stars. This is why quasars can be so bright. They are nature's most efficient power plants, turning destruction into illumination. TON 618's quasar glow is what revealed its existence to astronomers. When light from its distant core was first analyzed, it was immediately clear that something extraordinary was happening. Its spectrum showed intense emission lines from ionized elements like carbon, magnesium, and hydrogen, all broadened and shifted by the extreme velocities of the gas orbiting the black hole. By studying these lines, scientists could infer not only the temperature and composition of the accreting material, but also the staggering speed at which it moved, thousands of kilometers per second. Such high velocities could only be explained by the presence of a gravitational force on a scale far beyond that of any star or cluster, the unmistakable signature of a supermassive black hole. But what truly makes TON 618 stand out among quasars is its sheer scale and luminosity. Its light output is estimated to be over 140 trillion times brighter than our Sun, making it one of the most radiant objects ever detected. This means that in 1 second, TON 618 releases as much energy as our Sun would produce over millions of years. Even more incredible is the fact that this light began its journey roughly 10.4 billion years ago. The photons we detect today were emitted when the universe was still in its youth, when galaxies were just beginning to form, and the first heavy elements were spreading through space. TON 618's quasar radiance is so extreme that it challenges the limits of what astronomers thought possible. The energy being released near its core is likely approaching what scientists call the Eddington limit, the maximum luminosity a black hole can sustain before the outward pressure of radiation balances the inward pull of gravity. If the energy output exceeds this limit, the intense radiation can blow away infalling material, slowing or even halting further growth. The fact that TON 618 shines so close to this theoretical boundary suggests it's accreting matter at an extraordinary rate, pushing the laws of physics to their very edge. Studying quasars like TON 618 has transformed our understanding of the universe. They are not just exotic phenomena, they are key pieces of the cosmic puzzle. Quasars help astronomers trace the distribution of matter across space and time, probe the conditions of the early universe, and even measure the rate at which the cosmos expands. The light from quasars passes through intergalactic gas on its way to Earth, allowing scientists to analyze that gas and learn about its composition billions of years ago. In this way, quasars act as cosmic lighthouses, illuminating the history of everything between us and them. In TON 618's case, that light is more than a clue. It's a declaration of power on an almost incomprehensible scale. Every flicker of radiation from its accretion disk tells a story about gravity, motion, and the limits of nature itself. From the Tonantzintlo Observatory's early surveys to modern-day telescopes that analyze its spectral lines in exquisite detail, TON 618 continues to challenge our understanding of how black holes form, grow, and shape their galaxies. Yet while the discovery of its quasar nature revealed its presence, understanding its true magnitude required something more. To comprehend just how colossal TON 618 is, astronomers had to measure its mass, a task that involved unraveling the dance of light and matter swirling around it from billions of light years away. What they found would redefine the limit of the possible and cement TON 618's place as the largest black hole ever known. Measuring something as vast and distant as TON 618 might seem like an impossible task. After all, this object lies more than 10 billion light years away, and by its very nature, a black hole cannot be seen directly. It swallows light, time, and everything that ventures too close. So how do astronomers determine the size and mass of something that cannot be observed in any traditional sense? The answer lies in studying the light that surrounds it, the spectral fingerprints of the glowing matter being devoured by the black hole's immense gravity. When matter spirals toward a black hole, it forms a rapidly rotating accretion disk, a blazing whirlpool of gas and dust heated to millions of degrees. This disk emits light across the electromagnetic spectrum, from radio wave to visible light to X-rays. But more than just light, it also emits information. Embedded within that light are patterns, emission lines, created by specific elements as they are heated, ionized, and accelerated by the black hole's gravity. By studying these emission lines, astronomers can measure the velocity of the material orbiting near the black hole, and, from that, infer the mass of the unseen monster driving the system.
The principle is simple yet profound. The faster the gas is moving, the stronger the gravitational pull must be. The gravitational force is directly tied to the mass of the black hole. By observing how wide these spectral lines appear, they are Doppler broadening, caused by gas moving at extreme speeds, scientists can calculate just how fast the material is orbiting. Combine that speed with the distance from the black hole, estimated through luminosity and other modeling, and you can estimate the black hole's mass using the same basic physics that describe planetary orbits, Newton's and Einstein's gravitational laws on a cosmic scale. For TON 618, this analysis was done using optical and ultraviolet spectra obtained from detailed observations. Its light shows distinct, broadened emission lines of elements such as hydrogen, carbon, and magnesium, all shifted due to its enormous distance and the expansion of the universe. By measuring these lines, astronomers determined that the gas near its core was moving at incredible velocities, tens of thousands of kilometers per second. To accelerate gas to such speeds requires an object of truly staggering mass. The calculations pointed to a number so large that it initially seemed almost implausible. TON 618's central black hole was estimated to have a mass of approximately 66 billion times that of our Sun. That figure places it among the most massive black holes ever identified, possibly the most massive that has been reliably measured. To grasp how enormous that is, consider that Sagittarius A, the black hole at the heart of the Milky Way, has a mass of about 4 million suns. TON 618 is roughly 16,000 times more massive. Even the supermassive black hole in galaxy M87, the one whose shadow was famously imaged in 2019, weighs only about 6.5 billion suns, barely a tenth of TON 618's estimated mass. If you could somehow replace our Sun with TON 618, its event horizon, the boundary from which not even light can escape, would extend well beyond the orbit of Pluto. In fact, its diameter would be roughly 195 billion kilometers across, large enough to engulf our entire solar system multiple times over. That event horizon, known as the Schwarzschild radius, defines the point of no return. Anything within that radius, light, gas, stars, is lost forever, drawn into the singularity at the black hole's heart. To put this in even more startling perspective, if TON 618 were placed where our Sun currently sits, its outer edge would stretch far past the orbits of Neptune and the Kuiper Belt, possibly brushing the distant reaches of the Oort cloud. Every planet, asteroid, and comet would lie well within its gravitational grasp. It's a mind-bending scale, one that forces us to rethink what large even means. But TON 618's size isn't just impressive in a physical sense, it's also significant in a cosmic timescale. The light we see from TON 618 today was emitted about 10.4 billion years ago, when the universe itself was less than a third of its current age. That means TON 618 already formed and reached its monstrous size when galaxies were still young. For it to have grown so massive so early poses an enormous challenge to our understanding of black hole formation and evolution. Black holes grow primarily by two processes: accretion, feeding on surrounding gas and dust, and mergers, colliding and combining with other black holes. Both take time, often hundreds of millions or even billions of years. Yet TON 618 seems to have reached tens of billions of solar masses astonishingly quickly. To grow to such a size, it must have consumed material at a furious pace,
possibly far above the theoretical limit known as the Eddington rate, which defines how quickly a black hole can accrete matter before radiation pressure pushes new material away. If TON 618 indeed exceeded this limit, it might have done so during an era when the universe was denser, filled with gas-rich galaxies and frequent mergers, a cosmic feeding frenzy that allowed supermassive black holes to balloon in mass far faster than we once thought possible. Some astrophysicists suggest that TON 618 may have started as a direct collapse black hole, forming not from a dying star, but from the gravitational collapse of an enormous cloud of primordial gas, perhaps weighing hundreds of thousands of solar masses from the start. Others theorize that it could have grown through repeated mergers of smaller black holes in the early universe's chaotic environment. Whatever the case, its existence remains an unsolved riddle that challenges current cosmological models. The techniques used to study TON 618 also highlight one of astronomy's greatest paradoxes. We learn the most about black holes not by observing them directly, but by studying what they destroy. Every photon of light that reaches us from TON 618 has been twisted, heated, and accelerated by gravity's relentless pull. The very radiation that makes it visible is produced by the matter that's on its final journey towards oblivion. That means, in a strange and poetic way, the brightest object we've ever found in the distant universe is powered by darkness itself. It's through this interplay of light and gravity that TON 618 has revealed its secrets, a cosmic dance that lets us peer across billions of light years and glimpse the scale of one of nature's most extreme creations. Yet while these measurements give us a number, 66 billion solar masses, they don't quite convey the full reality of what that means. Numbers alone can't capture the immensity of something that defies all intuition. To truly comprehend it, we must compare it to the things we know, our sun, our solar system, our galaxy, and then imagine how small they seem beside this unfathomable colossus. To truly grasp the scale of TON 618, numbers alone are not enough. The human mind struggles to comprehend magnitudes that surpass everyday experience. When astronomers describe TON 618's mass as 66 billion times that of our sun, it's easy to understand it in an abstract sense, but the reality is even more mind-bending when we translate that into tangible dimensions. One of the clearest ways to visualize a black hole size is through its event horizon, the boundary surrounding the singularity from which nothing, not even light, can escape. For TON 618, this boundary is imaginably vast, stretching across approximately 195 billion kilometers. To put that in perspective, the distance from the Sun to Pluto is roughly 5.9 billion kilometers. TON 618's event horizon is more than 30 times that distance, large enough to swallow our entire solar system and then some, with room for spare for dozens of other solar systems alongside it. Another way to visualize this immense scale is by comparing it to the Sun, the closest star we know intimately. The Sun has a diameter of about 1.4 million kilometers. TON 618's event horizon is roughly 1,300 times larger, making our Sun appear almost microscopic by comparison. Not a star, but a tiny spark beside this cosmic furnace. If you were to place TON 618 in the center of our solar system, its outer edge would extend far past the orbits of Neptune and the Kuiper Belt, possibly brushing the outer boundaries of the Oort cloud. Every planet, asteroid, and comet would lie well within the black hole's gravitational grasp. It's a mind-bending scale, one that forces us to rethink what large even means. Even more staggering is to consider the volume. The event horizon of TON 618 isn't a solid sphere, but if it were, the sheer volume enclosed would be so enormous that the combined mass of all the planets, asteroids, and comets in our solar system would be vanishingly small by comparison. The scale is almost impossible to intuitively picture. Our entire star cluster in the Orion arm of the Milky Way would seem like a tiny speck against TON 618's colossal boundary.
The mass and size of TON 618 also redefine our understanding of density in extreme objects. While its singularity is infinitely dense, a point where all that mass is compressed to zero volume, the spatial scale defined by the event horizon gives the black hole a sort of presence in the cosmos. It isn't just an invisible point in space. It occupies a region so vast that its gravitational influence stretches across tens of billions of kilometers.
warping space-time and influencing the motion of stars and gas over unimaginable distances. If we continue the comparison to other well-known cosmic objects, the magnitude of TON 618 becomes even more apparent. Consider Sagittarius A, the supermassive black hole at the center of our galaxy, which has a mass of roughly 4 million suns. Its event horizon is about 12 million kilometers across, minuscule compared to TON 618. M87, the first black hole ever directly imaged, measures roughly 38 billion kilometers across. While enormous in its own right, M87 is still about 5 times smaller than TON 618. These comparisons place TON 618 in a league of its own, not just as the largest black hole discovered, but as a benchmark for cosmic extremity, a singularity whose scale borders on the incomprehensible. Even trying to think about the orbital distances of nearby stars or potential planets stretches the imagination. In a hypothetical scenario where TON 618 replaced the Sun, Earth's orbit at about 150 million kilometers would be negligible. Even Neptune, orbiting at roughly 4.5 billion kilometers, would lie well inside its event horizon. The gravitational well of TON 618 is so deep that objects far beyond what we consider the boundaries of a solar system would feel its influence. Its tidal forces, though subtle at extreme distances, could reshape entire star clusters, bending trajectories and reshaping galactic structures. This numbers game doesn't stop with distance comparisons. It also extends to time and energy. The swirling accretion disk near TON 618's event horizon rotates at near light speed, causing time dilation effects that are almost unimaginable. A second experience near the edge of TON 618 could equate to years for a distant observer. And the energy radiated from the accreting material is so intense that it dwarfs the combined light of thousands of typical galaxies. This means that TON 618 is not only a giant in size, but also in power, radiating energy on a scale that is utterly alien compared to familiar stellar objects. Even when considering the wider cosmic neighborhood, TON 618's scale is staggering. Its gravitational influence extends over light years, potentially affecting the movement of gas clouds, stars, and even neighboring galaxies in subtle ways. The mass alone ensures that any nearby material is inevitably drawn toward it, contributing to its growth and maintaining its status as a cosmic predator. The interplay between its size, mass, and gravity is a testament to how extreme physics becomes under such conditions, where the conventional rules of celestial mechanics give way to relativistic and quantum effects. Perhaps the most humbling realization from this comparison is just how small human perception is when faced with TON 618. Even our entire solar system, with its planets, moons, asteroids, and comets, is a mere fraction of the space occupied by this black hole's event horizon. Distances that feel unimaginably vast to us, billions of kilometers, are just a tip of the iceberg when scaled to TON 618. The black hole's enormity pushes the boundaries of comprehension, forcing us to rethink what it means for something to be large in the universe. In essence, comparing TON 618 to familiar cosmic landmarks allows us to begin grasping its true scale. It's not merely a black hole, it is a colossus of space and gravity, a singular entity whose dimensions eclipse the solar system, dwarf our sun, and stretch our understanding of size and power to their limits. Every metric, from kilometers to solar masses, emphasizes that TON 618 exists in a realm beyond ordinary experience, a reminder of the vast extremes the universe can create. It is not just a supermassive black hole, it is the ultimate benchmark for cosmic gigantism, a ruler against which all other black holes must be measured. TON 618 doesn't just challenge our understanding of size and mass, it also forces us to confront the staggering distances of the cosmos and the mind-bending implications of looking back in time. This black hole lies an astonishing 10.4 billion light-years away, which means the light we see today began its journey across the universe when our cosmic neighborhood was in its infancy. To put that into perspective, the universe itself is roughly 13.8 billion years old. So the photons reaching our telescopes from TON 618 were emitted when the universe was less than 3 times its current age, a time when galaxies were still forming, stars were relatively young, and cosmic structures were far less mature than they are today. In this context, TON 618 is remarkable not just for its size, but for the speed at which it grew. To reach a mass of 66 billion solar masses in such a relatively short time, it must have been consuming gas and dust at extraordinary rates, far exceeding anything seen in more nearby supermassive black holes. Its rapid growth challenges our understanding of how black holes and galaxies co-evolved in the early universe. Observing such distant quasars also allows scientists to study the intergalactic medium, the vast stretches of gas that fill the space between galaxies. As light from TON 618 traveled toward Earth, it passed through clouds of hydrogen, helium, and trace elements, some of which absorbed specific wavelengths. By analyzing these absorption lines in the quasar spectrum, astronomers can reconstruct the chemical composition, density, and temperature of matter in the early universe. In other words, TON 618 not only illuminates its immediate surroundings, but it also casts light on the cosmic environment across billions of light years. The sheer distance also has profound implications for cosmic expansion. Because the universe has been expanding since the Big Bang, the light from TON 618 has been stretched along the way, a phenomenon known as redshift. The wavelengths of emitted light become longer and shift toward the red end of the spectrum, providing astronomers with a direct measure of both distance and the rate of cosmic expansion. TON 618 has a redshift of approximately z equals 2.219, meaning the universe has expanded by more than 3 times since its light left that distant quasar. This makes TON 618 not only a monument to gravity and energy, but also a key marker for understanding the universe's evolution over billions of years.
It is important to realize that when we observe TON 618, we are seeing a snapshot of its ancient past. The black hole may have grown even more massive, or its host galaxy may have evolved dramatically in the intervening 10 billion years. Yet, we cannot see these changes directly because the light from such events has not yet reached us. Every observation of distant objects like TON 618 is a look into a universe long gone, yet still affecting the cosmos in ways we are only beginning to understand. The fact that TON 618 existed and had already achieved such enormous mass so early in cosmic history raises profound questions. How could a black hole grow so rapidly in a universe that was young and still forming galaxies? Theories include direct collapse of massive primordial gas clouds, frequent galactic mergers, and super-efficient accretion of material, all processes that may have been more common in the early universe than they are today. Observing TON 618 allows astrophysicists to test these theories, pushing the boundaries of our understanding of cosmic evolution. Even from 10.4 billion light-years away, TON 618 dominates its local cosmic environment. Its quasar brightness, over 140 trillion times the luminosity of the Sun, ensures that it is visible across intergalactic distances, acting as a lighthouse in the darkness of the early universe. Light from its accretion disks shines brighter than entire galaxies, illuminating gas clouds, star-forming regions, and even helping astronomers map the large-scale structure of the cosmos. In essence, TON 618 is not merely a massive black hole. It is a messenger from the distant past. Its existence tells a story about how matter, gravity, and energy interacted in the universe's youth. Observing it allows us to peer back into a time when the cosmos was younger, denser, and more chaotic than it is today. A time when supermassive black holes like TON 618 were beginning to establish themselves as the titanic engines that would shape the growth of galaxies and the evolution of the universe itself. By looking at TON 618, we are witnessing a cosmic paradox. We are seeing something unimaginably ancient, yet its physical scale dwarfs everything in the nearby universe. It's a bridge across time and space, a connection between the infant universe and the sprawling cosmos we inhabit today. And it is precisely this combination of distance, age, and power that makes TON 618 such a compelling subject for astronomers and the public alike. Its light, traveling for more than 10 billion years to reach Earth, brings us both knowledge and perspective, a reminder of the universe's vastness, the speed of light's limitations, and the incredible scale at which cosmic processes unfold. TON 618 is not just remarkable for its size or age, it is also staggeringly luminous, a beacon so bright that it defies ordinary comprehension. Its quasar, the blazing accretion disk of gas and dust spiraling into the black hole, emits light with a total energy output estimated at over 140 trillion times the luminosity of the sun. To put that in perspective, a single second of TON 618's radiation releases more energy than the sun would produce over millions of years. In terms of raw brilliance, it outshines entire galaxies composed of hundreds of billions of stars, making it one of the most radiant objects in the observable universe. This incredible luminosity arises from a process fundamentally different than that which powers ordinary stars. Stars like our sun generate light through nuclear fusion, slowly converting hydrogen into helium in their cores and releasing energy over billions of years. TON 618, by contrast, generates its energy not through fusion, but through gravitational accretion. Matter falling into the black hole loses gravitational potential energy, which is converted into heat and radiation as it accelerates and collides with other matter in the accretion disk. This process is astoundingly efficient, capable of converting up to 10% of the infalling mass directly into energy, a rate vastly higher than nuclear fusion, which converts only about 0.7% of mass into energy. The result is a powerhouse of light that far exceeds the collective energy output of every star in the Milky Way. The scale of TON 618's radiance is mind-boggling. Even if you were standing billions of light years away, the light arriving at your telescope would carry with it the signature of a colossal engine operating at near maximum efficiency. The matter in the accretion disk moves at tens of thousands of kilometers per second, heated to millions of degrees by friction and intense gravitational forces. At these speeds, collisions between particles release X-rays, ultraviolet radiation, and visible light, producing the spectacular energy output that astronomers detect across the cosmos. What makes TON 618 especially fascinating is that its light is not coming from the black hole itself. The black hole, by definition, emits no light. Its gravity traps photons as well as matter. Instead, the luminosity originates from the material just outside the event horizon, in the searing accretion disk. Here, matter is stretched, compressed, and heated to extremes, radiating energy before crossing the point of no return. Every photon that reaches Earth carries with it the story of matter's final moments before plunging into oblivion, making TON 618 a dramatic illustration of energy emerging from destruction. The energy output also manifests as relativistic jets, streams of particles launched at nearly the speed of light from the black hole's poles. While not all quasars produce visible jets, TON 618's activity suggests that immense magnetic fields near its accretion disk help funnel some of the infalling matter into these high-speed outflows. These jets can extend for hundreds of thousands of light years, illuminating intergalactic space and impacting nearby gas clouds and star-forming regions. In this sense, TON 618's influence is both luminous and far-reaching, shaping the environment of its host galaxy and beyond. TON 618's brightness allows astronomers to study a black hole that would otherwise be invisible across such distances. The quasar's light serves as a probe, revealing the chemical composition, motion, and dynamics of the material surrounding the black hole. By analyzing the spectrum, scientists can measure the velocities of ionized gas, estimate the mass of the central black hole, and infer how quickly it is feeding. These observations confirm that TON 618 is not only massive, but also in an extreme state of growth, devouring matter at rates close to theoretical maximums. The fact that a single black hole can outshine entire galaxies emphasizes the power of accretion physics. Stars shine through nuclear processes, and galaxies shine through the combined light of billions of stars. Yet a black hole's gravitational energy can exceed both by orders of magnitude. TON 618 demonstrates that gravity, when concentrated on a cosmic scale, can produce more light than countless suns combined. It is an extreme illustration of nature's efficiency, where the very act of destruction, matter being pulled into a singularity, creates unparalleled illumination. This brilliance also provides a crucial tool for cosmology. TON 618's light, traveling over 10 billion years to reach Earth, helps astronomers map the distribution of matter in the early universe. As its radiation passes through intergalactic gas clouds, specific wavelengths are absorbed, producing a pattern of absorption lines in the spectrum. These lines reveal the chemical composition, temperature, and density of the gas, offering a window into conditions billions of years ago. In this way, TON 618's luminosity is not only impressive, but also scientifically invaluable, providing insight into the formation and evolution of the early cosmos. Yet even as we marvel at its brightness, it's humbling to realize that TON 618's immense output is a byproduct of matter spiraling into darkness. Its light is a paradox. The brightest signal in the universe originates from the process of ultimate destruction. Every photon is a testament to the titanic forces that work near the event horizon, where gravity, velocity, and energy interact in ways that push the limits of physics.
In summary, TON 618 is not merely large or distant. It is the brightest of the bright, a quasar whose energy output eclipses everything around it. Its light reveals the immense power of gravitational accretion, the efficiency of matter converted into energy, and the dynamic, violent environment surrounding a hypermassive black hole. Even across billions of light-years, TON 618 outshines entire galaxies, illuminating the cosmos with a brilliance that continues to captivate astronomers and inspire awe in anyone who contemplates its scale. One of the most profound mysteries surrounding TON 618 is not just its size or brightness, but the astonishing speed at which it must have grown. The universe was less than a third of its current age when the light from TON 618 began its journey to Earth, meaning this black hole had already amassed a staggering 66 billion solar masses within just a few billion years after the Big Bang. In cosmic terms, this is an extraordinarily short period for a black hole to reach such a size. For astronomers, this raises a fundamental question. How can something so big exist in such a relatively young universe? The growth of a black hole occurs primarily through accretion, the process of matter falling into the black hole's gravitational well. In principle, the more matter a black hole consumes, the faster it grows. However, there are theoretical limits to this process. The Eddington limit defines the maximum rate at which a black hole can accrete matter before the outward pressure of the emitted radiation pushes infalling material away. Essentially, if a black hole tries to consume too quickly, the intense energy output creates a feedback mechanism that slows or halts growth. For TON 618 to reach tens of billions of solar masses in such a short period, it likely had to grow at or even above this theoretical limit, feeding at unprecedented rates in an environment rich with gas and dust. Another mechanism that could explain TON 618's rapid growth is galactic mergers. In the early universe, galaxies were smaller, denser, and far more chaotic than they are today. Collisions between galaxies were frequent, and these violent interactions could funnel enormous amounts of gas toward the galactic centers, fueling the black holes lurking there. Each merger also brings the central black holes of the colliding galaxies together, potentially forming a larger, more massive black hole. Over multiple mergers, this process can rapidly accelerate growth, effectively bypassing some of the time constraints imposed by steady accretion alone. TON 618 may have been a product of such a tumultuous cosmic environment, where both fuel supply and collisions were abundant. The concept of direct collapse black holes is another intriguing theory. Instead of forming from the collapse of a massive star, which typically yields stellar mass black holes, a direct collapse black hole could form from a pristine, massive gas cloud in the early universe, bypassing the initial small stages entirely. Under certain conditions, if a primordial gas cloud remains hot and dense enough without fragmenting into stars, gravity can cause it to collapse directly into a black hole with hundreds of thousands or even millions of solar masses. This provides an enormous head start, allowing a black hole to begin life already far larger than the remnants of ordinary stars, and thus grow more quickly into the supermassive giants observed in the early universe. TO-1618 may have originated from such a direct collapse, giving it a massive foundation on which to build its record-breaking mass. Some researchers also suggest that super-Eddington accretion might have played a role. Under specific circumstances, black holes could temporarily exceed the Eddington limit, consuming matter faster than traditionally allowed. In dense, gas-rich environments, radiation could be trapped within infalling material, allowing the black hole to ingest enormous quantities of matter without blowing it away. If TO-1618 underwent phases of super-Eddington accretion early in its history, it could explain how it reached tens of billions of solar masses in a fraction of the time required by standard growth models. The early universe itself may have favored rapid black hole growth. Shortly after the Big Bang, the cosmos was denser and more uniform, filled with vast amounts of cold, primordial gas. Galaxies were still forming, and conditions were right for black holes to acquire massive quantities of material with minimal resistance. This environment, combined with frequent galactic mergers and potential direct collapse origins, could have created the perfect storm for the formation of hypermassive black holes like TO-1618. Yet, even with these theories, TO-1618 remains a puzzle. It is one of the most extreme black holes ever discovered, and its sheer size and rapid growth continue to challenge cosmologists and astrophysicists. Its existence suggests that our understanding of black hole formation, early universe dynamics, and accretion physics may still be incomplete. Could there be unknown mechanisms accelerating black hole growth? Are there other hypermassive black holes even farther away, waiting to be discovered? TO-1618 pushes the limits of theory, forcing scientists to refine models and explore scenarios that previously seemed implausible. In contemplating TO-1618, we are reminded of the universe's capacity to produce extremes that stretch both the imagination and the laws of physics. A black hole so massive, so luminous, and so ancient, existing when the cosmos was still in its formative stages, is a direct challenge to our understanding of cosmic evolution. Its very presence forces a re-evaluation of what is possible in terms of gravitational growth, matter accumulation, and the early dynamics of galaxies. TO-1618 stands as both a beacon and a mystery, a record-breaking object that illuminates our universe while simultaneously exposing the gaps in our knowledge about how such monsters come to be.
Ultimately, the question of how something so big could exist touches on some of the most fundamental inquiries in astrophysics. It intertwines the physics of black holes, the history of galaxy formation, and the conditions of the early universe into a single, mind-bending narrative. TO-1618 is a testament to the universe's capacity for extremes, a cosmic paradox that combines incomprehensible mass, unparalleled brightness, and rapid formation into a single object that continues to awe scientists and ignite curiosity about the limits of nature itself. Approaching TO-1618 up close is an exercise in confronting the sublime extremes of the universe, a journey to a realm where gravity, energy, and space-time behave in ways that defy human intuition. While no spacecraft could ever survive the journey, we can imagine the spectacle that would unfold as we drew near. At first, from millions of kilometers away, TO-1618 would appear as an intense point of light, far brighter than any star or galaxy in our night sky. Unlike a single shining sun, however, this brilliance would not be steady. It would pulse and shimmer as matter swirled violently in the black hole's accretion disk.
The accretion disk itself is a cosmic whirlpool, a flattened, spinning structure of gas, dust, and stellar remnants spiraling inexorably toward the event horizon. Heated by immense friction and gravitational compression, the disk glows with X-rays, ultraviolet light, and visible radiation, forming a luminous ring that dwarfs the scale of entire solar systems. The closer the material is to the black hole, the faster it moves. Near the edge of the event horizon, particles orbit at velocities approaching the speed of light, releasing energy so intense that the disk blazes like a billion suns concentrated into a single, spinning circle of fire. The visual effect would be mesmerizing, a searing, swirling maelstrom of light, bright enough to blind anyone observing directly without protective shielding. At the poles of TON 618, the universe's raw power becomes even more dramatic through relativistic jets. These are beams of highly energized particles accelerated by magnetic fields near the black hole's rotation axis, shooting outward at nearly the speed of light. Stretching for hundreds of thousands of light years, these jets slice through the surrounding interstellar medium, emitting radio waves, X-rays, and gamma rays. From a safe distance, you would see them as colossal beams of energy glowing against the backdrop of space, a testament to the enormous forces at work in the black hole's vicinity. They represent a mechanism by which TON 618 channels some of the energy from accretion back into the universe, shaping gas clouds and even influencing star formation in nearby regions. At the very heart of this spectacle lies the event horizon, the boundary marking the point of no return. Beyond it is the black hole singularity, an infinitely dense point where space-time curves to its limits and our understanding of physics breaks down. The event horizon itself would appear as an inky black void, a spherical darkness surrounded by the luminous halo of the accretion disk. Light cannot escape from within, so this region remains completely invisible, a stark contrast to the blazing surroundings. Any object crossing this boundary would be irretrievably lost, stretched and compressed into a thin stream of matter in a process whimsically called spaghettification. The combination of brilliance and darkness would produce one of the most surreal cosmic sights imaginable. The gravitational field near TON 618 is so strong that it bends light, producing gravitational lensing effects. Photons from the backside of the accretion disk could curve around the black hole, allowing you to see multiple images of the disk at once, the entire spinning structure appearing to fold around the darkness at the center. Stars or gas clouds in the vicinity would also have their light distorted, creating warped, elongated images and rings around the black hole. This effect would give the entire system an otherworldly, almost artistic appearance, with luminous arcs and loops circling an absolute void. The scale of TON 618 adds another layer of awe. Its event horizon stretches across 195 billion kilometers, meaning the accretion disk itself would be hundreds of billions of kilometers across, many times the size of our solar system. The visual dominance of this structure would be unlike anything familiar. Planets, stars, and interstellar gas would appear small and insignificant compared to the blazing disk and the central black hole's gravitational shadow. Even light from nearby stars would be warped and stretched as it passed through TON 618's extreme gravity, creating shimmering distortions and arcs that would surround the accretion disk like cosmic ribbons. The jets, too, would be impossible to ignore. If you were oriented along the axis of one of the relativistic outflows, the energy beams would be so concentrated that they could incinerate anything in their path. From an angle offset from the jets, you would witness them as colossal streams of luminous particles, moving at near light speed and glowing brilliantly as they interact with the surrounding medium. They would serve as a vivid reminder that black holes are not just consumers of matter, but engines capable of injecting energy across intergalactic scales. Finally, the experience of being near TON 618 would not just be a visual spectacle, it would be a journey through the extremes of physics. Time dilation would become evident. A second near the event horizon could correspond to years for a distant observer. The gravitational forces would stretch, twist, and bend space itself.
The interplay of light, gravity, and matter would create an environment that is almost incomprehensible to the human mind, highlighting both the beauty and danger inherent in these cosmic monsters. In summary, approaching TON 618 would reveal a universe of extremes: a blazing accretion disk spinning at relativistic speeds, jets of energy piercing interstellar space, a black, inescapable void at its center, and a scale so vast that familiar structures like our solar system would appear microscopic. It is an awe-inspiring vision, a glimpse into the raw power and mystery of the cosmos, where matter and energy dance at the threshold of the unknown. TON 618 up close is not just a black hole, it is a cosmic spectacle, a vivid illustration of the forces that shape galaxies and illuminate the universe in ways that continue to both inspire and challenge human understanding. The physics surrounding TON 618 represents some of the most extreme and fascinating conditions in the universe, where gravity, energy, and time intertwine in ways that defy our everyday intuition. At its heart lies a supermassive black hole, an object whose mass is so immense that it warps the very fabric of space-time. To understand the phenomena occurring near TON 618, one must first appreciate the dynamics of accretion disks, relativistic jets, and time dilation, all of which illustrate the incredible forces at play.
The accretion disk is the primary engine of TON 618's luminosity. This disk forms as gas, dust, and other matter spiral toward the black hole, drawn in by its immense gravitational pull. As the matter accelerates inward, friction and collisions between particles cause it to heat to extraordinary temperatures, producing light across the electromagnetic spectrum, from visible light to X-rays and gamma rays. The innermost regions of the accretion disk move at velocities approaching the speed of light, which introduces relativistic effects. For instance, the side of the disk moving toward an observer appears brighter due to relativistic beaming, while the side moving away is dimmed. This contributes to the characteristic glow and spectral signatures astronomers detect when studying quasars like TON 618. Complementing the accretion disk are relativistic jets, which emerge from the poles of the black hole. These jets are streams of charged particles accelerated to near-light speeds by complex interactions between the black hole's magnetic field and the rotating accretion disk. They extend vast distances, sometimes hundreds of thousands of light-years, and carry enormous amounts of energy, shaping interstellar and intergalactic environments. Relativistic jets also emit radiation across the spectrum, from radio waves to X-rays and gamma rays, making them detectable across cosmic distances. In the case of TON 618, these jets highlight the immense energy processes taking place, where gravitational energy is efficiently converted into kinetic and radiative energy on a scale that dwarfs entire galaxies. Another crucial aspect of TON 618's physics is time dilation, a consequence of Einstein's theory of general relativity. In the intense gravitational field near the black hole, time behaves very differently from what we experience on Earth. The closer one approaches the event horizon, the slower time passes relative to an observer far away. Near TON 618's event horizon, even a single second for an object close to the black hole could correspond to years or even decades for a distant observer. This extreme time dilation is not merely theoretical. It has profound implications for understanding processes near black holes, including how we interpret the behavior of matter in accretion disks and the variability of quasar brightness. The gravitational environment of TON 618 also produces tidal forces that stretch and compress objects. Near the event horizon, these forces can be so strong that they spaghettify matter, elongating it into thin streams as it is pulled inexorably toward the singularity. These tidal effects, combined with extreme radiation and particle collisions, make the immediate vicinity of TON 618 an environment of unmatched violence and complexity. Magnetic fields play a pivotal role as well. In the inner regions of the accretion disk, magnetic field lines can twist and become extremely intense due to the rapid rotation of matter and the black hole's spin. These fields not only help funnel matter toward the event horizon, but also launch the relativistic jets, converting rotational and gravitational energy into directed streams of charged particles. The interaction between magnetic fields, rotation, and gravity is a key driver of the extraordinary phenomena that make quasars such as TON 618 both luminous and dynamic. Radiation pressure also significantly affects the behavior of matter near the black hole. As the accretion disk radiates enormous amounts of energy, this light exerts an outward force on infalling gas. When accretion approaches the Eddington limit, the balance between gravitational attraction and radiation pressure determines how efficiently the black hole can grow. In TON 618, this process is pushed to extremes, as the black hole accretes matter at a rate that likely hovers near this theoretical threshold, maximizing both its mass increase and its radiant output. Furthermore, TON 618 provides a natural laboratory for observing relativistic Doppler effects. Light emitted from the approaching side of the disk is blue-shifted, while light from the receding side is red-shifted, allowing astronomers to measure orbital velocities and infer the black hole's mass. These measurements, combined with the study of spectral emission lines, reveal not only the mass, but also the dynamics of the extreme environment surrounding TON 618, offering insights into the interplay between gravity, light, and matter under conditions unattainable anywhere else in the universe. Finally, the combination of extreme mass, rotation, and accretion near TON 618 produces phenomena that can shape entire galaxies. Its gravitational pull can influence the motion of stars and gas clouds for thousands of light years, while its relativistic jets inject energy into interstellar and intergalactic space, regulating star formation and affecting the distribution of matter. In this sense, the physics near TON 618 is not only a local spectacle, but a driver of cosmic evolution, linking the microscopic behavior of matter near the event horizon to the macroscopic structure of the universe. In sum, the physics surrounding TON 618 embodies the most extreme conditions in the cosmos: blazing accretion disks, near light-speed jets, tidal spaghettification, relativistic beaming, and profound time dilation. These phenomena illustrate the remarkable ways in which gravity, magnetism, and energy interact near a supermassive black hole. Observing TON 618 and studying these processes not only deepens our understanding of black holes, but also illuminates fundamental aspects of the universe itself, revealing how energy, matter, and time behave at the ultimate limits of physics. Given TON 618's immense mass and gravitational dominance, it is natural to wonder whether it might host stars, planets, or even entire clusters orbiting it at safe distances. While the extreme environment near the black hole is unquestionably inhospitable, with intense radiation, powerful tidal forces, and relativistic jets, gravity operates over vast distances. At sufficiently large separations, the gravitational pull of TON 618 could allow objects to maintain stable orbits, just as stars orbit supermassive black holes in the centers of more familiar galaxies.
In the cores of galaxies, supermassive black holes are typically surrounded by stellar populations and dense clusters. For instance, Sagittarius A, the Milky Way's central black hole, is orbited by dozens of stars known as the S-stars, some of which pass incredibly close to the event horizon yet survive their perilous journeys. If we scale this concept up to TON 618, the possibilities become even more extreme. With a mass of 66 billion solar masses, TON 618's gravitational influence extends across distances measured in hundreds of light years. Within this sphere, stars or even compact clusters could orbit stably, far enough to avoid destructive tidal forces, but still firmly under the black hole's gravitational grip. Any hypothetical planets orbiting such stars would have a very different environment from what we are familiar with. Even at safe distances from the black hole, the surrounding space would be bathed in radiation from the quasar's luminous accretion disk. The energy output of TON 618,
over 140 trillion times the luminosity of the Sun, would make nearby regions extremely hostile. Intense X-rays and gamma rays would likely strip atmospheres from planets, irradiate surfaces, and prevent the development of life as we know it. Yet, in theory, if a star or cluster were located at a distance of tens or hundreds of light years from the black hole, the gravitational bonds could remain stable, and planets orbiting those stars might survive, shielded from the worst radiation. The dynamics of such orbits would also be fascinating. Stars near TON 618 would move at tremendous velocities, with orbital periods possibly measured in hundreds or thousands of years, depending on their distance from the black hole. At closer distances, relativistic effects would become significant. Time dilation, precession of orbits, and gravitational redshift could all alter the appearance and behavior of these stars for an external observer. Clusters could form elongated orbits due to gravitational interactions, producing intricate patterns over cosmic timescales. The sheer gravitational pull of TON 618 could even strip stars from nearby galaxies, incorporating them into its own gravitational domain and creating an extended halo of orbiting matter. Moreover, TON 618's immense mass and energy output would influence interstellar gas clouds. Gas clouds falling toward the black hole could fragment into new stars at safe distances, creating a scenario in which star formation occurs in proximity to an extreme gravitational engine. These newly formed stars could then settle into orbits dictated by the black hole's gravity, creating a dynamic system where star formation, accretion, and gravitational interactions coexist. It's also worth noting that at sufficiently large distances, the radiation from the accretion disk diminishes, and the tidal forces weaken, allowing for a relatively stable orbital environment. Hypothetically, a planetary system orbiting a star hundreds of light years from TON 618 could maintain its structure for billions of years, unaffected by the catastrophic conditions near the event horizon. However, direct observation of such stars or planets is currently impossible due to the vast distance of TON 618, about 10.4 billion light-years from Earth, and the overpowering luminosity of the quasar, which outshines any potential orbiting objects by many orders of magnitude. In this context, TON 618 may not be entirely an isolated monster in space. Its gravitational sphere of influence could host a rich and complex system of stars, clusters, and gas clouds, all orbiting a central point of unimaginable mass. While the immediate vicinity near the event horizon is utterly inhospitable, the outskirts of this gravitational dominion could resemble scaled-up versions of galactic nuclei we observed closer to home. Here, gravity reigns supreme, dictating orbital paths and shaping the structure of stars and clusters over billions of years. In essence, TON 618 could serve as the central anchor for a vast, invisible system of orbiting matter. While planets close to the accretion disk would be destroyed, and stars within the relativistic jet cones would be irradiated and possibly torn apart, stars and clusters at safe distances could thrive in stable, long-term orbits. This raises fascinating possibilities for understanding the dynamics of hypermassive black holes and their role in shaping the environments of early galaxies, suggesting that even the largest and most extreme objects in the universe may act as gravitational architects, organizing and influencing the distribution of matter on grand scales. TON 618 is not only staggering in size and brightness, but also in the sheer scale of its gravitational influence. Its enormous mass of 66 billion solar masses gives it a gravitational pull that extends far beyond its immediate accretion disk, shaping the movement of matter across distances measured in tens to hundreds of light years. Unlike smaller black holes, whose influence is relatively localized, TON 618 acts as a dominant force over an entire region of space, controlling the motion of stars, gas clouds, and possibly even neighboring galaxies in its gravitational domain. Its presence defines the structure of its cosmic neighborhood in a way that is almost impossible to imagine from our solar system perspective.
To understand the scale, it helps to consider how gravity operates in space. gravity diminishes with distance. But for an object as massive as TON 618, this decline occurs over immense lengths. A star orbiting near the black hole might complete its revolution in decades or centuries, while a gas cloud tens of light years away could still be subtly pulled toward TON 618, influencing its trajectory and potentially funneling it into the accretion disk over millions of years. The sphere of influence, sometimes referred to as the black hole's gravitational reach or radius of influence, could extend for hundreds of light years, a vast territory where TON 618's pull dominates over the combined gravity of all other nearby stars. This massive gravitational field also affects interstellar and intergalactic gas, shaping the evolution of galaxies around it. Gas clouds that might otherwise drift freely can be captured, compressed, or redirected, creating regions of star formation or, conversely, stripping galaxies of the material they need to birth new stars. In the early universe, when TON 618 was already fully formed, its pull likely influenced the distribution of matter over enormous scales, helping determine the structure and growth of its host galaxy and possibly affecting neighboring galaxies in subtle ways. Essentially, it was not merely a point of mass, it was a cosmic architect, orchestrating the motion of matter over distances that dwarf even the scale of our Milky Way. The tidal forces generated by TON 618 also extend far beyond its immediate accretion disk. While these forces are most extreme near the event horizon, capable of stretching and tearing apart stars and gas clouds, they remain significant at greater distances, slowly deforming material over time. Large molecular clouds, even several dozen light years away, could experience gravitational stretching, causing them to collapse under their own weight or funneling parts of their mass inward toward the black hole. Over millions of years, these subtle forces help sustain the black hole's growth by providing a steady supply of infalling material. TON 618's gravity also warps space-time on scales unimaginable in the solar system. Near the event horizon, time slows dramatically, but even at distances far from the black hole, the curvature of space is noticeable on a cosmic scale. Light traveling near TON 618 is bent, producing gravitational lensing effects that magnify or distort the appearance of background galaxies. At distances of many light years, stars might have their apparent positions shifted or even produce multiple images as seen from an external vantage point. TON 618, in essence, becomes a massive lens, reshaping the light and matter around it simply through the influence of its gravity. The black hole's gravitational pull also has implications for galactic dynamics. A supermassive black hole of TON 618 size could anchor the core of its host galaxy so strongly that it dictates the motion of the innermost stars and clusters, creating tightly bound orbits in the galactic nucleus. Its influence can extend to the surrounding galactic halo, subtly controlling the trajectories of stars and star clusters, and possibly even affecting satellite galaxies orbiting the primary galaxy. This makes TON 618 not only a local gravitational powerhouse, but a key player in shaping the structure of its galactic environment, controlling matter on scales that span hundreds of thousands of light years. Furthermore, the gravitational dominance of TON 618 implies that it could capture stars or clusters from neighboring regions over time, adding to its mass and influence. Stellar interactions in the dense core of its host galaxy could scatter stars into trajectories that bring them within TON 618's reach, where tidal forces might strip them of matter or direct them into the accretion disk. Over millions of years, these subtle forces help sustain the black hole's growth by providing a steady supply of infalling material. In a more dramatic sense, TON 618's gravity demonstrates the limits of what is possible in the universe. Unlike ordinary stars, or even typical supermassive black holes, TON 618's presence can be felt across scales that encompass entire galactic neighborhoods. It is a cosmic anchor, a central force around which matter must navigate, whether in the form of stars, gas, dust, or entire clusters. Its gravity is so dominant that even over interstellar distances of dozens or hundreds of light years, the motions of objects are dictated by TON 618's pull, rather than the combined gravitational effects of other stars in the vicinity. In short, TON 618's gravitational scale is staggering. It reaches far beyond its event horizon, exerting influence across light years, shaping the trajectories of stars, guiding gas clouds into its accretion disk, and possibly even affecting the motion of stars and clusters in neighboring galaxies. Its gravity is not confined to the immediate vicinity, but extends outward, subtly and persistently molding matter across a vast cosmic domain. This immense influence underscores the black hole's role as both a local destructor and a galactic architect, demonstrating how one object can dominate space, time, and matter over distances that are almost impossible to conceptualize. When comparing TON 618 to other well-known supermassive black holes, its sheer scale becomes almost incomprehensible. Take Sagittarius A, for instance, the supermassive black hole at the center of our Milky Way galaxy. Sagittarius A has a mass of roughly 4 million solar masses, which is already enormous compared to stellar mass black holes. Its event horizon spans only 12 million kilometers, a distance that sounds vast but is infinitesimal compared to the cosmic behemoth that is TON 618. In stark contrast, TON 618's mass of 66 billion solar masses is over 16,000 times more massive, and its event horizon stretches across 195 billion kilometers, meaning it would easily engulf the orbits of all the planets in our solar system, from Mercury to Neptune and then some. The difference in scale is so dramatic that if Sagittarius A was a small dot on a cosmic map, TON 618 would appear as a colossal sphere dominating the entire scene. Similarly, consider M87, the black hole in the center of the Virgo A galaxy, famously imaged by the Event Horizon Telescope in 2019. M87 is already a titanic object, with a mass of about 6.5 billion solar masses, and its event horizon spans roughly 38 billion kilometers. This makes it nearly 10 times more massive than Sagittarius A, and its image revealed a glowing ring of light that offered humanity its first direct glimpse of a black hole's shadow. Yet even M87 pales in comparison to TON 618. TON 618 is over 10 times more massive, and its event horizon is more than 5 times larger, illustrating that while M87 impressed the scientific community, TON 618 truly redefines what it means to be a cosmic giant. The differences are even more striking when considered in terms of gravitational influence. Sagittarius A governs the orbits of stars within a few light years, such as the S stars in the Milky Way's core. M87, being more massive, exerts its pull over a much larger radius, controlling the dynamics of stars and gas across its central galactic region. TON 618, however, dominates a scale hundreds of times larger, influencing matter across tens or hundreds of light years, funneling gas and dust into its accretion disk, and possibly even affecting the motion of stars and clusters in neighboring galaxies. Its gravitational footprint is vast enough to dwarf the spheres of influence of Sagittarius A and M87 combined. Even when comparing luminosity, TON 618 leaves its peers far behind. Sagittarius A is relatively quiescent, producing little radiation compared to active galactic nuclei. And while M87 generates relativistic jets that are observable across millions of light years, TON 618's quasar output of over 140 trillion solar luminosities completely eclipses both of them. Where M87's jet is a spectacular feature, TON 618's radiation and energy output from its accretion disk are far more extreme, outshining entire galaxies and revealing the incredible power that comes with such extreme mass.
TON 618 also emphasizes the vast range of scales present in the universe. While stellar mass black holes, like those formed from collapsing stars, might measure just a few tens of kilometers across and have masses of only a few solar masses,
TON 618 exists at the other end of the spectrum. Comparing a stellar mass black hole, Sagittarius A, M87, and TON 618, is akin to comparing a pebble, a skyscraper, a small city, and a sprawling continent. The jump from one category to the next is enormous, but TON 618 occupies a scale so extreme that it challenges human comprehension and places it in a league of its own. This comparison also has implications for understanding galaxy evolution. While Sagittarius A and M87 influence the dynamics of their host galaxies and contribute to regulating star formation, TON 618, with its unparalleled mass and energetic output, likely played a dominant role in shaping its galactic environment during the early universe. Its extreme gravitational pull and powerful radiation would have affected the motion of stars, compressed or expelled interstellar gas, and possibly even determined the formation of nearby galaxies, making it not just the record-setting black hole, but a central architect in its cosmic neighborhood. In essence, TON 618 is the ultimate benchmark for black hole extremity. Where other supermassive black holes are awe-inspiring, TON 618 stuns the imagination. Its mass, size, luminosity, and gravitational influence are orders of magnitude beyond what we consider normal even among the giants of the universe. Comparisons with Sagittarius A and M87 highlight the dramatic gulf between ordinary supermassive black holes and the hypermassive leviathan that is TON 618, emphasizing that in the universe there are scales so extreme they challenge our very ability to visualize them. The existence of TON 618 naturally leads to a tantalizing question. If a black hole can reach 66 billion solar masses, could even larger ones exist elsewhere in the universe? The answer, based on current astrophysical understanding, is potentially yes. While TON 618 currently holds the record for the largest known black hole, the universe is unimaginably vast, containing hundreds of billions of galaxies, many of which are at distances far beyond our observational reach. It is entirely plausible that there are hypermassive black holes even more extreme than TON 618, hidden in regions of the cosmos we have yet to explore. One reason such giants might remain undetected is distance. TON 618 is already located 10.4 billion light-years away, meaning we are seeing it as it was in the early universe. Objects beyond this distance would have their light stretched even further due to cosmic expansion, making them fainter and more difficult to observe with current instruments. Additionally, extremely distant quasars may be obscured by dust and gas, concealing their radiation from telescopes on Earth. In such cases, even black holes more massive than TON 618 could exist unnoticed, quietly shaping the evolution of their host galaxies while remaining invisible to our eyes. Theoretical models also support the possibility of larger black holes. In the early universe, regions of exceptionally high gas density could have produced direct collapse black holes that began life with hundreds of millions of solar masses. Combined with rapid accretion, galactic mergers, and super Eddington growth phases, such black holes, over time, could reach masses surpassing TON 618. Some astrophysicists speculate that hypermassive black holes exceeding 100 billion solar masses might exist in the centers of the largest galaxies or proto-galaxies, particularly in regions where galaxy formation was highly efficient and gas was abundant. Another factor suggesting the potential for even larger black holes is the observed upper limit to black hole growth. While there is no definitive theoretical cap on mass, practical constraints exist. The Eddington limit regulates accretion rates, and feedback from quasar radiation can expel surrounding gas, limiting growth. However, in some environments, particularly in the dense, chaotic early universe, these constraints could be circumvented temporarily. Galaxies with unusually high gas inflow rates, repeated mergers, or favorable alignments might allow black holes to grow far beyond what we have observed so far. TON 618 may be just one example of a population of ultra-massive black holes awaiting discovery.
Observational biases also play a role. TON 618 was identified because of its extreme luminosity as a quasar, which makes it visible across cosmic distances. But what about black holes that are actively accreting less material or located in less luminous host galaxies? They may be invisible in electromagnetic surveys, effectively hiding their presence. Some of the most massive black holes may be silent giants, cloaked in regions where light cannot escape or where the surrounding gas has already been consumed or expelled. These black holes could rival or even exceed TON 618 in mass, but remain undetected simply because they do not emit the intense radiation that makes quasars like TON 618 stand out. In addition, the possibility exists for collisions between supermassive black holes. Galactic mergers can bring together two central black holes, and if these collisions occur in rapid succession, the resulting black hole could exceed the mass of any single progenitor. Over billions of years, hierarchical mergers could theoretically create black holes that dwarf even TON 618, especially in the centers of massive galaxy clusters where multiple mergers occur over cosmic time. Cosmological simulations also suggest that the largest structures in the universe, including massive galaxy clusters and cosmic filaments, could host these ultra-massive black holes. The most extreme environments, regions with exceptional density and sustained gas inflow, may be the breeding grounds for hypermassive black holes that surpass anything yet observed. Our current instruments are only beginning to probe these distant, dense environments, meaning discoveries of even larger black holes could lie just beyond the edge of what is currently detectable.
The mere idea that even larger black holes may exist stretches our imagination. If one were to find a black hole with 100 billion, 200 billion, or more solar masses, it would redefine our understanding of the upper limits of cosmic growth. Such a discovery would challenge models of black hole formation, accretion physics, and galaxy evolution, forcing astrophysicists to reconsider what is physically possible in the universe. TON 618 serves as both a benchmark and a hint that the universe may harbor even more extreme entities, some of which may forever remain hidden in the cosmic distance. Ultimately, the possibility of larger black holes highlights the vastness and mystery of the universe. TON 618 demonstrates that nature can create objects of unimaginable size, but it also suggests that this is not necessarily the ceiling. The universe is so immense and buried that somewhere out there, beyond the reach of current observations, even more colossal black holes may exist. Dark giants whose gravity governs regions of space that we may never directly see, yet whose presence helps shape the cosmos on a grand scale. TON 618's sheer mass and energy output place it at the very center of its cosmic environment, allowing it to play a pivotal role in shaping the cosmic web, the vast network of galaxies, gas, and dark matter that threads through the universe. Supermassive black holes like TON 618 are not isolated phenomenon. They exist in dynamic interplay with their host galaxies and their surrounding intergalactic medium. The enormous gravitational pull and energetic feedback from such a black hole can influence the distribution of gas, regulate star formation, and even sculpt the evolution of neighboring galaxies over millions of light years. At the heart of this influence is TON 618's capacity to control the motion of interstellar and intergalactic gas. Its gravitational reach extends across tens or even hundreds of light years, meaning that gas clouds in its vicinity are pulled inward, potentially fueling further accretion. As gas spirals toward the accretion disk, it heats up, producing the tremendous luminosity characteristic of quasars. But not all of this energy is absorbed by the surrounding matter. TON 618's output generates intense radiation pressure that can push gas away from the central regions, creating galactic winds and clearing out areas of star formation. This feedback mechanism is crucial in galaxy evolution because it regulates the amount of gas available for forming new stars, preventing runaway star formation that could destabilize the host galaxy. Beyond the host galaxy, TON 618 can also affect neighboring galaxies and intergalactic filaments. The jets emitted along the black hole's poles transport energy and high-energy particles across distances of hundreds of thousands of light years. These jets can compress gas in adjacent regions, triggering star formation in some areas while dispersing gas in others. In this way, TON 618 acts not only as a consumer of matter, but also as a cosmic architect, redistributing energy and matter throughout the surrounding regions and influencing the structure and evolution of the galactic neighborhood. Moreover, TON 618 likely plays a role in maintaining the balance of the early universe. During the epoch when TON 618 existed, roughly 10.4 billion years ago, galaxies were forming at a rapid pace. A hypermassive black hole like TON 618 would have been capable of stabilizing its host galaxy, preventing it from collapsing under its own gravity too quickly by moderating star formation rates and regulating the inflow of gas. At the same time, the radiation emitted by TON 618 could ionize surrounding gas, affecting the intergalactic medium and influencing the evolution of nearby proto-galaxies. Essentially, TON 618 acted as a central node in the early cosmic web, coordinating the flow of matter and energy in ways that help shape large-scale cosmic structure. The influence of TON 618 is amplified by its size and energy output. While smaller black holes can influence their immediate galaxy centers, TON 618's gravity and radiation extend across scales large enough to interact with clusters of galaxies. Its jets and radiation can travel vast distances, impacting intergalactic gas streams, compressing filaments of hydrogen, and potentially guiding the formation of future galaxies along certain trajectories. The black hole's presence can therefore imprint its influence on the architecture of the cosmic web, affecting how galaxies form, cluster, and evolve across millions of light years. TON 618 also demonstrates the coevolution of galaxies and black holes. Observations suggest that the growth of supermassive black holes and their host galaxies are intimately linked. The more massive the black hole, the greater its ability to regulate star formation and shape galactic structure. TON 618, as one of the largest black holes known, likely had an outsized role in this feedback process. Its gravity would anchor the galactic core, while its energetic output controlled the inflow and outflow of gas, ultimately influencing the mass, size, and stellar content of its host galaxy. In this sense, TON 618 is not merely a passive occupant of a galaxy center. It is a driving force in the evolution of cosmic structures. The black hole's influence extends to dark matter halos as well. Dark matter dominates the gravitational structure of galaxies, and by shaping the distribution of baryonic, normal matter, through radiation and gravitational pull, TON 618 indirectly impacts the arrangement of dark matter in its host galaxy. The redistribution of gas in stars in response to the black hole's activity may influence how dark matter halos collapse, merge, and stabilize, further affecting the evolution of galaxies over cosmic time.
In summary, TON 618 is a central player in the cosmic web. Its gravity captures and organizes matter on enormous scales. Its radiation and jets redistribute energy across intergalactic distances, and its presence regulates star formation in the early universe. It exemplifies the profound interconnectedness of cosmic structures, showing that even a single hypermassive black hole can shape galaxies, intergalactic gas, and the evolution of the universe on scales that are both vast and intricate. TON 618 is more than a black hole. It is a cosmic architect, a gravitational and energetic powerhouse whose influence reverberates far beyond its immediate surroundings. Visiting TON 618 is an impossible dream, not just because of its immense distance, 10.4 billion light-years away, but because of the extreme physical conditions near the black hole. Even if we could somehow traverse the unimaginable vastness of space at speeds far beyond anything humanity currently possesses, approaching TON 618 would place any traveler in an environment of absolute destruction, where the fundamental forces of the universe conspire to obliterate matter. The dangers arise from two primary factors: the gravitational forces near the event horizon and the intense radiation from its accretion disk and jets. The most immediate threat would be the black hole's tidal forces, which increase exponentially as one approaches the event horizon. These forces are so extreme that they would stretch and compress any object, including a spaceship or human body, in a process astronomers colorfully term spaghettification. Near TON 618, The difference in gravitational pull between your feet and your head would be staggering. Your body would be elongated into a thin thread-like shape as gravity pulls on the part of you closer to the black hole much more strongly than the parts farther away. Unlike smaller black holes, where tidal effects might be felt only near the final kilometers, TON 618's size means that these forces would become catastrophic at distances hundreds of thousands or even millions of kilometers from the event horizon. In essence, no matter how advanced a spacecraft might be, it would be torn apart long before reaching the center. Radiation presents an equally lethal hazard. TON 618's accretion disk emits over 140 trillion times the luminosity of the Sun, bathing the surrounding space in X-rays, gamma rays, and high-energy particles. Approaching the black hole would expose travelers to intense ionizing radiation, capable of destroying electronic systems, stripping away protective shielding, and instantly vaporizing biological tissue. Even if a spacecraft could somehow withstand the tidal forces, surviving the radiation environment is effectively impossible. The relativistic jets, shooting out at nearly the speed of light along the poles, represent additional hazards. Any trajectory that intersected with these streams of high-energy particles would be fatal, releasing energy equivalent to a supernova directly into the ship. Time dilation adds a surreal dimension to the danger. As one nears the event horizon, time slows drastically relative to the outside universe. For a traveler approaching TON 618, seconds could stretch into years from the perspective of a distant observer. While this might seem like a minor inconvenience compared to spaghettification and radiation, it underscores the extreme distortion of reality near such a massive black hole. The very fabric of space and time is warped, creating an environment fundamentally hostile to any matter or technology attempting to approach. Even if one attempted to orbit TON 618 at a safe distance, far from the event horizon, the scale of the gravitational pull would pose navigational challenges unlike anything experienced elsewhere. Orbits would be fast, highly elliptical, and relativistically distorted, requiring near-perfect precision to avoid being pulled inexorably inward. Any miscalculation, even by a fraction, could result in the spacecraft being drawn toward the accretion disk and eventually into the singularity. There is literally no margin for error. TON 618's gravity is absolute and uncompromising. Speculating further, if one somehow managed to hover just outside the event horizon without being destroyed, a theoretical impossibility, the visual spectacle would be awe-inspiring yet terrifying. The black hole's gravity would bend light dramatically, causing stars behind it to wrap around the darkness in arcs and rings. The accretion disk would blaze with unimaginable intensity, and relativistic jets could streak across the sky at nearly light speed. But this beauty comes at a price. The radiation alone would sterilize anything within sight, and the tidal forces would make sustained observation impossible. TON 618's environment is both magnificent and lethal, an ultimate example of nature's extremes. In the cosmic context, TON 618 serves as a stark reminder of the limits of exploration. No matter how advanced civilization becomes, no spacecraft could survive close approach. It is a monument to forces far beyond human control, a place where the laws of physics exert themselves with relentless intensity. Spaghettification, radiation, and gravitational dominance ensure that TON 618 remains an untouchable entity, a remote observer spectacle rather than a destination for physical exploration. Ultimately, the impossibility of visiting TON 618 emphasizes its scale and danger. It is a cosmic leviathan, exerting power over matter and energy across billions of kilometers. The environment around it is lethal on every front. Gravity stretches, radiation incinerates, and time itself warps in ways that defy comprehension. TON 618 can only be studied from afar, through its light, jets, and gravitational influence, offering a window into extremes that no human or probe could ever safely enter. It is both awe-inspiring and terrifying, a reminder that the universe contains forces so powerful that direct contact is impossible.
TON 618 is more than just a record-breaking black hole. It is a cosmic laboratory that teaches us invaluable lessons about the universe, pushing the boundaries of what we understand about physics, gravity, and galaxy formation. One of the most immediate insights TON 618 provides is about the limits of cosmic growth. Its sheer mass, 66 billion times that of the Sun, challenges existing models of black hole formation and accretion,
forcing astronomers to reevaluate how matter can accumulate at such staggering rates in a relatively short cosmic timespan. Observing TON 61A allows scientists to explore the extreme end of black hole evolution, revealing that under certain conditions, the universe can produce objects far larger than previously imagined. By studying it, we begin to understand the efficiency and scale of accretion processes, the role of galactic mergers in growth, and the potential for direct collapse mechanisms in the early universe, all of which inform theories about how other supermassive black holes may form. TON 618 also sheds light on galaxy evolution. Supermassive black holes and their host galaxies are closely linked, evolving together through complex interactions of gravity, radiation, and gas dynamics. The enormous energy output from TON 618's quasar, for instance, illustrates how black holes regulate star formation by heating or expelling gas from the surrounding galactic nucleus. By analyzing TON 618, scientists gain insight into how hypermassive black holes can shape the structure of their host galaxies, influence intergalactic gas, and even impact the formation of neighboring galaxies. Its existence underscores the idea that black holes are not merely endpoints of stellar evolution, but active participants in cosmic architecture, guiding the distribution of matter and energy across scales spanning hundreds of thousands of light years. From a physics standpoint, TON 618 offers a window into the behavior of matter under extreme gravity. Near its event horizon, matter is accelerated to relativistic speeds, subjected to enormous tidal forces, and heated to temperatures that generate high-energy radiation observable across billions of light years. By studying the emission spectra from its accretion disk and the properties of its relativistic jets, scientists learn how matter behaves in the most extreme gravitational fields possible, approaching conditions where general relativity and quantum effects intersect. Observations of time dilation effects and gravitational lensing around TON 618 allow us to test predictions of Einstein's theory in a regime far beyond anything achievable on Earth or in the solar system, giving unprecedented insights into how space, time, and light are warped by extreme mass. Furthermore, TON 618 informs our understanding of the early universe. At a distance of 10.4 billion light-years, we are seeing it as it existed when the universe was still young, less than a third of its current age. This allows scientists to investigate how black holes and galaxies evolved in the first few billion years after the Big Bang. TON 618 exemplifies that hypermassive black holes could have formed remarkably quickly, indicating that the conditions of the early universe, dense gas, frequent galactic mergers, and high rates of accretion, were conducive to extreme growth. Studying TON 618 therefore helps cosmologists refine models of early cosmic structure formation, the emergence of quasars, and the interplay between gravity, radiation, and matter in the formative epochs of the universe. Beyond its technical and theoretical importance, TON 618 also teaches us about the scale and diversity of the cosmos. Comparing it to more familiar supermassive black holes like Sagittarius A or M87 underscores the vast range of possibilities in the universe. TON 618 pushes our imagination, showing that the universe can produce objects of unimaginable mass and energy that operate on scales dwarfing entire solar systems and even entire galaxies. Its quasar output, over 140 trillion times the luminosity of the Sun, illustrates the immense energy that matter can release as it falls into a black hole, providing a tangible demonstration of how gravity can convert mass into radiant energy with extraordinary efficiency. In addition, studying TON 618 allows astronomers to explore the limits of observation and measurement. Detecting and analyzing such distant and luminous objects requires advanced techniques in spectroscopy, gravitational modeling, and high-energy astrophysics. By learning to measure the mass, velocity, and accretion dynamics of TON 618, scientists refine methods applicable to other black holes and galaxies, improving our overall understanding of the cosmos.
In this sense, TON 618 is both a target of study and a tool, enhancing our capability to observe and interpret phenomena across billions of light years.
Ultimately, TON 618 serves as a reminder of the extremes of nature. It challenges assumptions about what is possible in the universe, demonstrates the interconnectedness of gravity, matter, and energy, and illuminates processes that shape galaxies and cosmic structures. Studying TON 618 deepens our understanding of physics under extreme conditions, informs models of galaxy formation and evolution, and provides a window into the early universe. It is not merely a distant object of curiosity, it is a cosmic benchmark, a key that helps unlock fundamental truths about the universe's formation, behavior, and the extraordinary forces at play across space and time. Its lessons reverberate across disciplines, inspiring awe and expanding the boundaries of scientific knowledge, reminding us that the universe contains structures and phenomena far beyond anything we experience on Earth. TON 618 stands as one of the most extraordinary objects ever discovered, a cosmic giant that challenges every measure of scale and imagination. Its name, seemingly simple, a catalog designation from the Tonantzin Observatory, belies the staggering reality it represents. A black hole 66 billion times the mass of our Sun, with a gravitational pull that dominates its surroundings across hundreds of light years, and a quasar luminosity so immense it outshines entire galaxies. To contemplate TON 618 is to confront the extremes of the universe, to recognize forces and scales that dwarf everything familiar in human experience, from planets and stars to even entire solar systems. It serves as a humbling reminder of our smallness, not only in distance, but in mass, energy, and temporal perspective. In the cosmic tapestry, TON 618 is more than just a singularity or a black hole. It is a monument to the universe's creative power. It exemplifies the way matter and energy interact under the most extreme conditions, how gravity sculpts galaxies, and how the universe can produce objects of unimaginable mass in a relatively short span of cosmic time. Its blazing accretion disk, relativistic jets, and gravitational dominance are not just features, they are manifestations of the extraordinary physics that govern the cosmos, highlighting both the beauty and the peril inherent in such extremes. Even from billions of light years away, TON 618 communicates its power, sending us photons that traveled more than 10 billion years to reach us, messages from the early universe encoded in light. Beyond its scientific significance, TON 618 also inspires awe on a profoundly human level. It confronts us with the scale of the universe in ways that are almost impossible to internalize. Our entire solar system could fit within its event horizon many times over, and yet it is but a tiny node within the vast cosmic web that TON 618 helps shape. Imagining its accretion disk spinning, its jets cutting across intergalactic space, and its gravitational pull sculpting the motion of stars and gas evokes a sense of wonder that transcends mathematics and physics. TON 618 is a vivid illustration that the universe is not static or tame. It is a dynamic arena of extremes, full of giants and forces far beyond human experience. TON 618 also embodies the limits of human exploration and understanding. No spacecraft could approach it without being destroyed, and even our most powerful telescopes can only observe its distant light and infer its properties. Yet, in this remoteness, it offers profound lessons. By studying it from afar, we learn about the growth of supermassive black holes, the evolution of galaxies, the behavior of matter under extreme gravity, and the distribution of energy in the early universe. It represents the intersection of observation, theory, and imagination, pushing science to its limits while reminding us that the universe is far more immense and mysterious than we can fully comprehend. TON 618 is a black hole, yes, but it is also a mirror of cosmic ambition, reflecting both the enormity of nature and the human drive to explore, to quantify, and to marvel at the universe.
Ultimately, TON 618 is not just a number, a catalog entry, or a distant astronomical object. It is a cosmic giant that embodies the extremes of mass, gravity, energy, and scale, a reminder of how small we are in comparison and a source of endless wonder and inspiration. Its presence underscores the vastness and complexity of the universe, revealing realms where matter, energy, and time interact in ways that are almost beyond imagination. TON 618 invites us to dream bigger, to study deeper, and to gaze upward with humility and awe, recognizing that even in the farthest reaches of space, there exist entities that redefine the limits of possibility and remind us of the incredible richness of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.